This is the beginning of the final set of notes for the year, which is kind of wild that we have made it.
Beginning of the final. Let's go. Time to lock in.
Yes. Beginning of the end. Yes, that's what we'll call it.
We'll be like, this is chapter 9.
We're already recording.
Okay.
Unit 9.
Here we go. Okay. This is unit 9. This is unit 9. The end of the beginning of the end.
That was really good.
That was good.
That was really good. The end of the beginning of the end. It's okay. Anyways, if you saw the reminder or any of the things I posted the last 2 days, it's okay if you haven't.
I have. I just didn't read it.
Okay. We have lab lunch tomorrow. So, lab tomorrow. We will also go over the test tomorrow because everyone will have taken it by then. So,
Derek, what'd you get?
it's related to this.
How wasn't as bad? I got a million. Were you generous?
I got a million.
I was generous.
I assumed you were generous. Way more than
I'm always generous though.
Yeah, true.
I thought you already got a million.
Okay. So here we go. As I was saying, it is the final countdown. Okay. I just had to. I had to. Thank you. Thank you. So, what is entropy? Do you remember those charts at the end of the book?
Yeah.
And there was like 2 other columns. We only used one of them. We're coming back to that now. The good news is it's not that bad. I've been advertising this as not that hard. Agreed? Yes. It's not. Yeah, it's not that bad. But do you guys remember what entropy is? Disorder. Yes.
Holy crap.
So the disorder of a system. Did you read ahead?
We did this in physics too.
Oh, physics too. Yeah, that makes sense. Yes. So it is disorder. One may assume, and we know what assuming does, that a reaction with a. You guys get that joke? Okay, it's fine. I didn't know that till a couple years ago.
What?
What happens when you assume?
Oh yeah.
You can whisper it to her. I can't say that out loud on one may assume that a reaction with a negative delta H value always proceeds since. Had you ever heard of that before? Okay.
I don't get it.
A-S-S-U-N.
If you spell it,
Oh! I get it.
it's kind of like
Diddy, why are you gonna pass that Diddy like that?
As if.
it's kind of like jack acetate. Yeah, it's kind of like jack acetate. So, all right, let's lock back in. You're actually just spelling out the word. Yeah. Okay. One may assume that a reaction with a negative delta H. What does a negative delta H mean? Exothermic. Correct? Which means how does that feel to you? Hot. Would always proceed since the products have lower energy than the reactants and are more stable. They're also more stable. That's why matter reacts, right? But, this isn't always so. If a reaction has a very blank activation energy, high, has a very high activation energy, it will not occur. And that is described as kinetically stable. So we're talking about kinetics. What do kinetics mean? Movement, right? We're talking about movement of particles. What did you say? Well, that is, temperature is a measure of the average kinetic speed of a substance, yes. Or under kinetic control. In this case, one may predict the reaction would produce very little products. Here's an example. So we have the oxidation of ammonia by O2 to produce NO and H2O. So what does that look like? The delta H for the reaction is negative 909 kilojoules per mole, showing that ammonia and oxygen are very unstable, but the reaction doesn't proceed since the activation energy is so high. Therefore, the reactants are considered stable, and nothing will happen until the activation energy is met. You guys would agree negative 909, that's almost like 1,000 kilojoules per mole, right? That's a lot. It is, but it doesn't happen until you go over that what? You got to go over the hump. Yes. So one would also assume reactions with a positive delta H will never proceed since the products have a higher enthalpy. Because remember, delta H is called enthalpy. Then the reactants are less stable. But that also doesn't hold true. This means that delta H and activation energy are not the only factors, that blank, that determine whether a chemical reaction will or will not take place. Will or will not take place. So, consider the following reaction. So we're going to have potassium chloride dissolving. So here is KCl, which is a solid. If I'm going to dissolve it, what am I going to add it to? Water. H2O, which is a liquid. Let's just say this goes to the right for now. It doesn't matter how you write it. And that gives me KCl, which is now AQ. And let's give this a delta H of positive 19.2 kilojoules per mole. So if I look at the above equation, I see that there is a change from a relatively ordered or organized solid. You would agree that potassium chloride is a solid, yes? What type of solid is it? Say that louder. Ionic. It's Daniel's birthday! Happy birthday to you. Happy birthday to you. Happy birthday, dear Daniel. Happy birthday to you. Happy birthday. Time to get the hat out. The hat is... It is hydration break as well. Happy birthday.
Yes.
You have been crowned the birthday hero for the day.
Wow.
Wow. Wow.
Wait, can you stand in front of the camera for a minute?
Do you want to?
How
What?
do we know?
Okay, he wants to be documented of
Okay,
the...
we have to retitle it now. Daniel's birthday can't be beginning with the end.
The
Look,
beginning.
there it is.
Beginning.
There it is. There it is. Daniel has made his appearance. What happens? Oh, I'm sorry. All right, I will hydrate. I'm going to take one myself.
Is the first year of teaching the hardest because you have to write all your lesson plans?
Oh, the first like 3 years.
Or do you just steal lesson plans from other teachers too?
Well, like you're like kind of following what other people are doing.
He just buys it from us. Yeah.
But like a lot of times you have to be careful. Like I didn't have like there's something called like teachers pay teachers out there.
Yeah.
It's like teachers like making stuff. But like if you're like buying that stuff and not like trying it out first, there could be mistakes on it. Like anyways,
This stuff you get now, you just use it every year pretty much.
once you get it down and you know what you're doing, but I didn't start notes 3 years ago. Like I was still giving like all paper. It was way too much writing. Like you just couldn't write it all. So, Grady, what am I doing tonight? I'm not sure. Why? Where?
Here.
The turf is done? Oh, lacrosse. Lacrosse is done. Which I saw them working at the softball and baseball fields too.
Yeah, there.
So, tonight,
I'm going.
what time?
6:30.
My wife got the plague that everyone else has got.
Bonnet plague.
Well, it's not the real plague, but you know, the sickness.
What's down with the sickness?
Yeah, she got the sickness.
Like norovirus or?
I don't know. She's getting tested for strep and flu at the doctor, probably right now. So we might need to get out of the house. Maybe we'll stop by for like a beautiful night of lacrosse.
Varsity probably gonna be like the first 2 quarters. There's 6 quarters.
Okay. Okay. What time?
Yeah,
Maddie now can't have After we lock it. Wait, what time is it?
6:30.
quarters.
You might have to be like.
Oh wait.
Okay.
Yeah.
Grady, when's it start? Grady, when's it start?
$1.50. We're doing $1.50 today.
Do I have to pay?
No.
Okay. All right. Anyways, back to chemistry. Thank you, Ava. Appreciate it. Daniel had just said an ionic solid. And we know that ionic solids are what structure? Crystal lattice. There we go. We're getting the callbacks, which is good. All right. So you would agree if I'm going from crystal lattice to ions floating, that is a definitely less ordered or disorganized, yes? To a less ordered or disorganized state, which is a solution. The degree of dispersal of energy in a reaction, so we're going to actually define it now, is called entropy. So there's several things way to define this. The degree of dispersal of energy, the disorder, however you want to think about it, but that is called entropy. And is given the symbol S. Couldn't be E, because we probably already used E for what? Energy, yeah.
It should be K. It should be K.
We can't use K. We know what happens with that, Lucy, okay? Just saying. We've used,
Assuming too much with the K's.
and the funny thing is, you would think we've used all the Ks. I think we got one more K this chapter. I know. It's crazy. So, in the reaction above, there has been an increase. Agreed? An increase in entropy, which means the matter in this equation has become more dispersed. And therefore, delta S is positive. So, for delta S, for entropy, when it is positive, it's more disordered. When it is negative, it is less disordered, which means more ordered, right? Yes, it is. The hardest thing about delta S and delta G, which we're going to talk about in a second, is remembering the positive negative.
Wait, can you repeat what you said? Yeah.
So delta S, if it is positive, that means it is more disordered. Okay? If delta S is negative, it's less disordered, also known as more ordered. Okay? So, like I said, the hardest thing about delta S, delta G is just remembering the positive negative. Okay. So, the universe always tends towards greater entropy, kind of like your bedroom at home. All right? Why? What happens to your bedroom at home if you don't clean it? Keeps getting messy. What do you have to do? What do you have to do to clean your bedroom? Put energy in. So, now you got it, okay? If you do not continually put more energy in, it's just going to keep doing what? Spreading, getting worse, dispersing. The universe is expanding. So, now we're really talking to deep, physics, universe, all that stuff. But the universe tends towards entropy, all right? Unless you put more energy in.
Doesn't entropy always increase though?
If you don't put more energy in to organize it, then yes. That's what I'm saying.
Isn't that the second law of thermodynamics?
That's the second law of the first law is matter cannot be created or destroyed.
Conservation of energy.
Right. Second law is everything gets more disorganized. So, yes. Speaking of,
For knowing basic things.
what's that?
He got credited for knowing common sense.
It's okay. Well, the second.
Not him, not him.
Oh, who got credit?
The what thing?
Who got credit?
The person who dropped the apple and.
Newton?
Yeah.
Why are you just assuming he got on the ground?
I thought we were talking about Kevin. We went from Kevin to Isaac Newton.
I thought you were just blaming Kevin.
Why are you giving Kevin credit for knowing the second law of thermodynamics? Common sense. Oh my gosh. Anyways, I was about to say,
Not Kevin. Way to make us feel
Kevin's being
bad.
toxic.
listen, this is being proven in my house right now. Our playroom has gotten disastrous because they've been doing beads all week. You can't even walk in there. It's a disaster. It's a disaster. There's beads all over, and they're organized piles too.
By color.
Oh, it's color, shape, letter. It's a mess. It's a mess.
It's a disorder.
What's that? It's a disordered mess. Yes. I just try not to go in there and think about it. Eventually, we'll just have to say you got to clean it up. And then they'll clean it up, and then 5 minutes later, entropy. Right. It just happens. So, a pure, this is kind of cool. Perfect crystal at 0 Kelvin. What's the problem so far?
Absolute zero.
That's impossible. Okay. AKA absolute zero, because we cannot reach that on Earth, would have 0 entropy. So if you had a perfect crystal, right, perfectly organized, because the crystal structure is a good structure, it's perfectly organized, and there was no particles moving, right? Because at 0 Kelvin, there's no particle movement, that's 0 entropy, which is impossible. So you can either just get more disordered or less, but you're never going to hit 0. Yes?
So how do you have a negative entropy then?
Negative entropy means it's getting more ordered on that scale.
Oh.
From 1 Kelvin, right.
I was thinking that.
You can have a negative entropy, that just means it's getting more ordered.
So that's not delta S.
That is delta S. If delta S is negative, your substance is becoming more ordered. If delta S is positive, it's becoming more
But
disordered.
isn't that already perfectly ordered? It's like how do you get
This would be entropy of 0. So what you're doing for entropy, you're comparing entropy before and after is what you're doing.
okay.
So
So you can't
that's
get
your
like-
question.
You can't get like the
So nothing's happening.
You'll never get 0 entropy. So you'll have an entropy for your products, entropy for your reactants. You're going to subtract them and compare. Yes.
So if delta S is negative, then delta H would be positive.
Not necessarily. You're getting ahead of me. Okay? Soon, we're going to talk about that. Because we're going to talk about delta G too. And then you compare all three, and then you determine all that stuff. Okay, that's where we're heading. Okay. Yeah, do you want to go off on her?
You're like, why would you even move ahead? We're not even there yet.
It's toxic. That's all I can say.
You know the.
All right, so a crystal at 0. Who else is absent today besides Ella? Is it just Ella?
Yeah.
Ella, I hope you're enjoying this. This is very entertaining so far. We miss you. Okay.
I thought you said shut up.
Yeah, because everything is through your toxic filter right now.
Yeah,
So,
This is us. No, me and Haley, you just never know what we're gonna say.
okay. All right, so perfect crystal, perfectly organized, completely ordered. All entropies in the real world are measured relative to this, which means must have a delta S greater than 0. So that's your question, Danny. Yes, all delta S will be greater than 0, but you can show a change in delta S that's either positive or negative, which is what we're going to be calculating. So, aqueous ions are measured to a relative different 0. So could have negative values, but you're not going to see that in an AP test. I just want to throw that in there. Okay, flip it.
Got a bunch of lines?
Flip it. Yeah, we're going to fill those lines up. So let's talk about our delta S. My delta S for solids would be less than my delta S for liquids, which would be way less than my delta S for what?
Gases.
Gases. G-A-S, is it S-S-E-S? So, organized, less organized, very disorganized. What else can we talk about delta S? My delta S for a low number of particles would be how for a high? Less than or greater than? Be less than the delta S for a high number of particles, right? Because if I have less particles, right, I get less disorder. What else could I talk about? Delta S of gas. Yep, you're on the right track. Gases with a small volume, aka Audrey, a high pressure, is going to be what for gases with a large volume? Less than or greater than? Less than. Less than delta S for gases, you got it, at a high volume. Why? Because at a high volume, what can the particles do? They spread. So put in parentheses, the particles will spread. Lastly, delta S increases with the increase of, as Audrey was saying, temperature. Why? What happens as temperature goes up? Particles move faster. So far, this is pretty conceptual, right? Not that bad. So predict the sign of delta S in these reactions. Try 1 and 2, negative or positive. Predict the sign of delta S on 1 and 2, negative or positive. Oh, my wife has flu. Oh, that's the worst.
Shout out Heller's wife, feel better.
Yeah.
You might need some baby coffee.
Why would you get sick? Why would you even think about doing that? Why would you get the flu? Why?
I don't even know if you can take anything for flu.
How
Like
fast
Tamiflu?
did they-
Get
Yeah.
out and get some.
What?
Depends how fast they caught, like, on.
I mean, she just had a fever this morning.
Then she might go get Tamiflu.
Okay.
Get some
I think it
fresh
has to
air at
be.
the lacrosse
I think it has to be
game.
like 24 to 48 hours.
We're going to want to be out of the house. So,
Woo! Go, Worcester Lax.
did you predict
Oh, shoot. What?
I did in my head.
in your head? You don't want to write it down.
Because I can.
Okay. First one, delta S. I have a solid and a liquid going to a solid. Negative or positive? Negative. Why? This is more ordered. I have a solid and a liquid on the left. I only have a solid on the right. And there's going to be a more numerical way to calculate this in a second. Here, I have a solid going to a solid and a gas. What's that going to be? Positive. More disordered. More disordered. Okay, which of the following has greater entropy? A metal at 273 or the same metal at 400?
Increase with the increase.
Entropy is disorder. 400. Why?
Temperature increases, more particle movement.
Particles moving faster. A flexible soft metal like lead or diamond, which is a rigid solid. Soft metal like lead. Because a diamond has a crystalline structure. Okay? Two samples of the same gas at the same temperature, but one with a pressure of 1 atm and the other with a pressure of 0.5 atm. Why? Less pressure, more room for them to spread. More disorder.
Nice.
Okay.
Okay? So, the change in entropy, which is going to be my delta S at standard conditions in a reaction, can be found by subtracting the sum of the absolute values of entropy of the reactants, this should sound familiar, from the sum of the same for the products. This reaction is going to look very similar. So that means that delta S equals the sum of the entropies of the products. Remember, you take the moles and you multiply it by the number, right? Minus the sum of the entropies of the reactants. It's always products minus reactants, except for which calculation this year was the opposite?
The one that we just had, like,
Product over reaction.
The one that was reactants minus products was bond energies,
oh, shoot.
because that was bonds broken minus bonds formed. So that's the only one that's not products minus reactants. I know. That's why we need like a long time to review. Yeah. Oh. Okay. So here's a quick example to work through, and I have given you all of the numbers. So do it. I gave you the equation. Solve for delta S.
The coefficients matter.
You have to multiply by the number of moles. Okay, she got Tamiflu. So,
Is that good?
that's good.
Because that'll take away like half a percent.
How did she get her fever down?
You gotta get out in the air.
If
gotta-
not, she
you gotta
needs
get
to
some
take
fresh
like,
air.
I don't know if Tylenol's in it. Because my dad's yapping about all these people getting the flu.
Can't even on the news or something, just like complain about like random stuff. And like, I'm getting mad at that. I'm like, what do I
Unless she's like, my dad. My dad's like, oh, you're fine.
No, that's.
Oh, you're fine.
Not, but,
Yeah, you don't
know
get
that, but I just, let's be real.
Yeah.
Yeah, it should be negative.
Yeah, I got negative 199.
Yeah, I don't got it.
I think we should ask Danny what it is because he can do mental
Hell,
math.
did you get 199?
Well, before we do any calculations, we're gonna need some music. I can't calculate this unless I've got music. So,
Cute.
It should be 199.
Oh, yeah. Downloaded. Wait, we could just sing it.
dun, dun, dun.
There we go.
Shoot, why is it look like he's like timed and he's like, so he's like for like a rocket ship?
The reading, I did it, so I did the second. I didn't do the second to last batch, but I came back to it and but I got that.
Get ready, you have a lot of volume. Get ready, you have a lot of volume.
What?
H2 is 131.
Okay, I literally just have -1.
So there's my math. So I got 2 moles times 193 minus 1 mole times 192 plus 3 moles times 131. Delta S, what did you guys get?
-199.
Negative 199 joules per what?
Mole.
Nope.
Entropy, S.
Nope. It's just joules per Kelvin. Because I took moles times joules per Kelvin mole. So I have joules per Kelvin.
Yeah.
Is that what we would have expected? I went from, so this is saying that I had a negative delta S, so I got what? More ordered. Does that make sense according to my equation? How many moles of gas on the left? How many on the right? More ordered. So that works. Oh shoot, here we go. See, you can tell that I wrote this because I was getting ahead of myself. We could have predicted the value would be negative, because the system became more ordered or less disordered, however you guys want to think about it. 4 moles of gas, that should be arrow. The arrows never work on this. Change to 2 moles of gas. Okay, so now let's start combining some new stuff with some old stuff. So enthalpy and entropy, things we've talked about, are brought together in the Gibbs-Helmholtz. That's actually a name, not Pivnert.
The bonus question.
Free energy equation. Usually you just say Gibbs. All right? Poor Helmholtz. All right? That guy got just too much.
Were
Too
they the
much.
same person? Or different?
No, Gibbs and Helmholtz were 2 different
Okay, on
dudes.
this last test, one of the bonus should be what is Pivnert? And a person is the right answer.
A person? Well, it's not the right
What if
answer.
our last test is just like brain rot from the class?
It's like the AP Chem teacher.
We got to start working on the t-shirt soon.
Like, what is one thing that was on the?
We need to take a lab lunch to mock it up.
We do need to take a lab lunch, so I agree. Delta G equals, this is important. That's Gibbs. That's a G. Delta H minus, what are you talking about? That's a G.
It's a capital G.
Oh, a capital.
Minus T delta S. So delta E equals delta H minus T delta S. That is the most important equation probably for the rest of the chapter. This is easy, okay?
We didn't solve for it. We
Yes.
got to that.
Standard conditions. So that's 298 Kelvin and 1 ATM. Every time I keep seeing Daniel's horn, I keep thinking his hand is up. I'm like, why does he keep raising his hand? But it's his birthday unicorn thing. Please consider the following. So, in order to apply this equation, all reactants and products in an equilibrium, so equilibrium is still part of this, mixture must be at their standard, thank you for asking that question, what that zero was, states. Meaning gas is at 1.0 TM, like I just said, 1.0 ATM, and solutions at 1.0 molar. So we haven't talked about molarity, but standard for molarity is 1 molar. A temperature should be stated, and is usually, as I just said, 298 Kelvin. Entropy values tend to be given in units that involve joules. But, this is the big but. Enthalpy is usually given in what?
Degrees.
Kilojoules per mole. This means you're going to have to do some conversions. So, it's not that bad. It's easy, right? So you're either going to be multiplying or dividing by what? 1,000. All thermodynamically favored. After that, right up here, put spontaneous.
Okay.
All right? So if you are thermodynamically favored, I like to say that you are spontaneous.
Do you think I'm thermodynamically?
Are you spontaneous? Well, then yes. All right? Have a value for delta G that is negative. Like I said, hardest thing on this is remembering your positives and negatives. So entropy negative means it is what? More ordered. Delta G negative means it is spontaneous. All right? Means it's spontaneous. So, the math of the equation above tells us that delta G is going to be favored by a what? So, if I want to be spontaneous, right? If I want this to be negative, what do I want my delta H to be? Think about that. Positive or negative? Negative, right? Because if I take a negative, yes, and I subtract a positive from it, a negative minus a positive is more. That's all you're figuring out here. Okay? So, and what for my delta S, positive or negative? Positive. Why? Because a negative, can temperature be, this is Kelvin temperature by the way, can that be, that can't be negative. So negative minus a positive is more what? Hence, it is more spontaneous. Okay? So what you're going to be looking at are different values here and determining, is it spontaneous or is it not spontaneous? That's it, which is part of tomorrow's lab. Our thermodynamically favored equation may be very slow if the, what? Blank blank is high. It's two blanks. Activation energy, yes. If the activation energy is high. So that means it may be spontaneous. We have to actually talk about what is spontaneous. Spontaneous means once the action begins, it just goes. No energy is required to be put in order to make it keep going. That doesn't mean there's still an activation energy you still have to go through. It just means that spontaneous is it keeps running. Is that okay? Okay. So a reaction that has a negative delta G may not occur at a measurable rate. At a measurable rate. If this is true, the thermodynamically favored reaction is said to be under kinetic control. So, here is your analysis of possible sign combos of delta H, delta S, delta G, which gives us the following summary. So, If delta H is positive, what am I doing with heat? I'm taking in heat. So I'm taking in heat. So heat in, heat in. If delta H is negative, I am releasing heat, right? I'm releasing heat. Or you could say heat out. If delta S is positive, that means I'm becoming more what? Disordered. So more disorder. Here I have less disorder. Let's just label all these quick. More disorder. And then we'll probably call it a day after this. Less disorder. After we talk through this chart. So, if delta H is positive and delta S is positive, delta G could still be negative if I have a really high temperature, right? Why? If this is high, right, if it's big enough, I can still have a positive minus a positive that gives me a negative. All right? If I have a positive delta H and a negative delta S, think about that. Delta G is always non-spontaneous because I have a positive minus a negative, which is a positive, plus a positive. Next one. If I have a negative delta H, which is a negative, and a positive delta S, always negative, and then you can see if I have a negative and a negative, it depends on the temperature. Cool? We will continue that tomorrow. Wait, how much time do we have left? Wait, let's finish this last sentence. Because look, it says this would be a good time for a lab. Let's finish this. This is perfect timing. Okay? If delta G is positive, then the reaction isn't thermodynamically favored. That means my reactants are favored. And if it is 0, then the reaction is favored in both directions, which means it is at what? Equilibrium. So this is another way to determine equilibrium. Also, delta G equals the sum of delta G of the products minus the sum of the delta G of the reactants. So it's the same equation. So if delta G is 0, it's at equilibrium. So another way to determine equilibrium. That's a good place to stop. Because look, good time. Look at that.
Great.
Perfect timing. I thought we'd get to that point today. Because this next thing is kind of a new idea.